All right. Well, hello, everybody. Happy Wednesday to you. Glad you found this. Um, Today's a big day. We're going to be learning some of the formulas so we can stop doing derivatives the hard way. But to do them the easy way, we're going to have to use the hard way to get there. So basically, I'm going to show you where a whole bunch of rules come from, hopefully in a way that's fairly concise and also informative. And then at the end of the day today, we'll know how to take the derivative of any polynomial and one little bonus function that we'll get to as well. So I am going to dive right in. The derivative of a constant. We know that a constant, f of x equals c, it's just a horizontal line. So the answer should be 0, but I thought this would be a good one for me to do to, I guess, show you the way that I'm going to be going about this, and that is using the definition of a derivative that says, the derivative is the limit as h goes to 0 of the function evaluated at x plus h. And so in this case, f of x plus h minus f of x all over h. And this is, I should be very clear about this, this is the derivative. This is f prime. Well, if f of x is equal to c, if my function is a constant, then f of x plus h is c. F of x is c. I mean, that's no matter what you plug in, the output of this function is a constant. So this is really equal to the limit as h goes to 0 of c minus c over h, which is the limit as h goes to 0 of 0 over h. Now, as h goes to 0, of course, the denominator is going to 0. At 0, it doesn't exist. So thinking in terms of limits, as I plug in values of h that are close to 0, 1, 0.1, 0.01, negative 0.1, 0.01, we always have 0. 0 divided by anything is 0, except for when h is equal to 0. But we don't care about that. We don't care about the value at 0. So our answer is that the derivative is equal to 0. Quick, easy, that's what we were expecting. So that's what this is going to look like. Derivative of a constant, a function with a constant multiple. So I'm going to start using a little bit more correct notation here. The derivative of g of x will be equal to, well, here we go. This is going to be the limit as h goes to 0 of my function evaluated at x plus h minus my function evaluated at x all over h. F of x minus h minus f of x all over h. And so this is g prime of x will be, let's take a look at what's happening here. In my numerator, both of these terms have a constant in them. So I can factor that out. I can say that this is the limit as h goes to 0 of that constant times, I'm applying some limit rules here, limit laws that say I can do the limit of a product as the product of the limits after I factored stuff out. I've got the limit as h goes to 0 of f of x plus h minus f of x all over h. The limit of a constant is the constant, and this limit as h goes to 0 of f of x plus h minus f of x all over h, that is the derivative of f. And so that's what we're getting. We're getting that derivative of a constant times a function is equal to the constant times the derivative of the function. It basically says if I've got a 5 in front of some function, and if I want to differentiate that, I can just treat the 5 separately. I can just ignore the 5, leave the 5 for later, and just differentiate the function. We'll apply this in a moment, but right now, well, we need more rules before we can get to some more interesting derivatives. So bear with me. We will definitely get to some examples in a moment. The derivative of a sum or a difference. Boy, I think I'm going to leave this one for the book to justify. It's the same thing that I've just been doing. Express it as a limit. Use the commutative property that lets you move things around, but I think I'm going to skip right to the punchline and say that what you are hoping is going to happen is going to happen. If I have a function that is two different things added together, I am allowed to treat them both separately and just do the derivative of the first plus the derivative of the second. And again, if you want justification for why that is a thing, there is a write-up in the book, and I'd be happy to do it individually, but I think I'd rather take more time on the next one. And by the way, subtraction works the same way. If this is a minus sign, and this is a minus sign. Sum and differences both work the same way. Derivative of x to the n. Here's where things are going to get interesting. Here's where I think I'm going to have to switch over and go to my document camera. Okay, here we go. F of x equals x to the n power. So I'm going to start with the same limit notation that we've been doing. The derivative of f of x is equal to the limit as, h goes to 0 of f of x plus h minus f of x all over h. This is restating just the definition of a derivative. And so if I write that out using our function, in this case, x to the n power, I've got x plus h to the n minus x to the n all over h. And so now the tricky part of this, and I better make sure my h's look like h's so they don't get confused with n's. X plus h to the n power is a little bit tricky. And so I'm going to set this aside quick, and I'm going to give you a quick refresher on something called binomial expansion that's going to require the use of Pascal's triangle. I'm going to remind you that if I have something like a plus b to the 6th power, this is something you would have done, well, either in Algebra 2 or possibly in functions in trig, maybe even pre-calc where you might have seen this. I know I'd certainly do this in those classes. I also touch on this in Math League. To do to the 6th power means I need the 6th row of Pascal's triangle. So just a reminder of what Pascal's triangle looks like. It's a set of ones on the outsides, and then everything else is the sum of the two digits that are right above it. So 4 comes from 1 plus 3, 10 comes from 4 plus 6, etc. And so the 6th row of Pascal's triangle, 1 plus 5 is 6, 5 plus 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and then a 1 to finish it off. And so this a plus b to the 6th power, I'm going to use these as my coefficients. These are going to be the 7 coefficients of this expansion. I'm going to have 1 times something plus 6 times something plus 15 times something plus 20. Let's see, I'm going to run out of space there. So we'll just go to the next row, plus 15 times something, plus 6 times something, plus 1 times something. These are just the coefficients. And then the terms are going to be either increasing or decreasing powers of a and b. And so I'm going to start with a to the 6th power, and then have a to the 5th, a to the 4th, a to the 3rd, to the 2nd, to the 1st, and to the 0 power, which is just 1. I've got decreasing powers of a, which means I'll have increasing powers of b. I'm going to go to the end and say it's going to end with b to the 6th, preceded by b to the 5th, b to the 4th, b cubed, b squared, b to the 1st, and nothing. And so there's the expansion. If you were to multiply a plus b times a plus b times a plus b 6 times and FOIL that whole thing out and then FOIL it again, and we're not even FOILing because it's not just binomials, but if you expanded that whole thing, this is what you would get. This was a plus b to the 6th power. Notice I was using the coefficients in the 6th row of Pascal's triangle. In the 3rd row, it starts with 1 and then a 3. In the 5th row, it starts with 1 and then a 5. In the nth row, it's going to start with 1 and then an n, and then something that ends up being a little bit more complicated. Now, it turns out that this term right there, the 2nd term of Pascal's triangle, this is 6, choose 2. For reasons that aren't important for us right now, these numbers actually turn out to be the results of a combination. This is 6, choose 0, 6, choose 1, 6, choose 2, 6, choose 3, etc., until we get to 6, choose 6, which is 1. And so these are combinations that, again, is something that you've learned in the past. Exactly what they are doesn't make all that big of a difference, but just keep in mind that the first two terms are 1 followed by the number of the row we're in, followed by some other things that are the result of combinations. So back to our derivative of x to the n power, I'm going to handle this x plus h to the n by considering what we just saw with Pascal's triangle. I'm going to say that our derivative is the limit as h goes to 0. I'm going to make sure my screen still looks all right. Of, here we go, x plus h to the n power. Well, we saw what a plus b to the 6th was. X plus h to the n, the first term is going to be 1 times x to the highest power. In this case, it was 6. If n is my power, then it's going to be 1 times x to the n power and h to the 0. The next term came from Pascal's triangle. In the 6th row, the second coefficient was 6. In the nth row, our second coefficient is n. So my next coefficient is n times, and now I've got my decreasing powers of x. It was x to the n, so now it's x to the n minus 1. And then I'm going to have, in this case, we had a plus b. I'm expanding x plus h to the n. So I had b to the 0. We'll have h to the 0. B to the first, b to the second, b to the third, etc. And so my powers of h are going to be to the 0, to the 1, h to the 1, and then my next term. Now my next term, again, this isn't going to be a huge deal, but this coefficient that we're missing here, in terms of n, it's a combination. It turns out to be n choose 2. 1 is n choose 0. N is n choose 1. This coefficient is n choose 2. And now my powers of x, I've got x to the n minus 1, x to the n minus 2. Whoops. And then my powers of h, I've got h to the 0, h to the 1, h to the 2. At this point, I'm going to put some ellipses and say that the rest of these terms are all going to be something like this. Something times x to some power times h to some power, at least as big as 2. And then at the very end of all of this stuff, we're going to have this final from the formula for the derivative, x to the n. All of that stuff is divided by h. Now, all of these ellipses, these are a bunch of terms, however many terms we have. If n is 15, then I've got probably about 13 different terms that are taken up by these ellipses. But what they all have in common is that they are something times x to some power plus h to some power that's bigger than 2, because I've already written that one down. So when I go ahead and start simplifying this, the limit as h goes to 0, I've got x to the n minus x to the n. That's gone. I've got n times x to the n minus 1 times h plus n choose 2, x to the n minus 2, h to the 2, plus a whole bunch of terms that all have a whole bunch of h's in them, among other things. And so what I have at this point is I've got every term in my numerator has an h in it. The only terms that didn't have an h have canceled each other out. And so I've got a bunch of terms that have an h in them. So I'm going to cancel one of these h's. I'm going to take away one of those h's. All the rest of these, there's an h to the third term that now becomes h to the second. There's an h to the fourth term that becomes h to the third. Canceling out with the h in the denominator. All of my h's in the denominator have canceled out with one of the h's in each of the terms on the top, which brings me to limit as h goes to 0. Let's see, I will have n times x to the n minus 1 times 1 plus n choose 2, whatever that is, x to the n minus 2 times, now I've got h to the 1 plus a whole bunch of terms that all have an h in them. And so if h is going to 0, nothing happens to this term because there's no h's, and all of the rest of the terms would have at least one h. If h is going to 0, all the rest of these terms are going to 0, which means all we have left, and we evaluate this, is n times x to the n minus 1, which is a pretty big deal. We just found that the derivative, if f of x is x to the n, The derivative is n times x to the n minus 1. And now I think it's time for us to get some practice. Okay, back to this software. We've got our derivatives. At this point, we have the ability to take the derivative of any polynomial that you could possibly ever see. Something times x to some power minus something times x to some power plus something. Here we go. Here's what we're going to do. I'm going to say that this derivative, f prime, is going to be, we learned that the constant times a function, the derivative of a constant times the function is the constant times the derivative of the function. We just learned that the derivative of x to the n is n times x to the n minus 1. So the derivative of x to the third is 3 times x to the 3 minus 1, which is 2. We learned that if I want to take the derivative of this thing plus this thing plus this thing, I'm allowed to break it up and do them separately. So I can continue on and say the derivative of 3 times something is 3 times the derivative of the something. In this case, the derivative of x squared, the derivative of x to the 2 is 2 times x to the 1. I'll just call that x. And then we also learned that the derivative of a constant is 0. So we end up with plus 0 at the end. And then we can simplify and say that this is 12x squared minus 6x, and we are done. There we go, the derivative of a polynomial. Now, most of you, when you do these problems, instead of doing 4 times 3x squared, you're going to just multiply these and say that this is 3 times 4. This is 12x to the 2 minus 6x to the 1. And then the derivative of a constant is 0. The next one I want to take a look at is right here. I can't, there we go. Sorry, something that you can't see was getting in my way. I've got this one. Go ahead, pause the video and go ahead and do this one. If you're following directions, you paused and now you are back and you've already done this. So I'm going to go through this fairly quickly and say that the derivative will be 2 times 324. That's 648 x to the 323 plus the derivative of x to the 7, which is 7x to the 6th, plus 0. If you fell for it, don't feel bad. This is the first time, but don't fall for this again. Pi is a number. 5 times pi cubed is a constant. The derivative of a constant is 0. And there we go. We got another derivative. In your assignment, you're going to see problems that don't look like polynomials. And right now, we don't know how to do the derivative of anything except for polynomials. So when you see something like this, you may be tempted to say that the derivative of this thing times that thing is the derivative of this thing times the derivative of that thing. Don't do that. It may not be true. On Monday, we'll find out that it is not true. But even if it might be true, we don't know that it's true, so we shouldn't apply a rule that we don't know to be true. So instead, I'm going to do what I do know is true, and that is I can rewrite this. I'm not taking the derivative yet. I'm just going to rewrite this as 2x to the 5th minus 5x cubed. I'm going to write it in a form that I know how to differentiate. I'm just distributing that x to the 3rd, just like you've been doing since Algebra 2. And so now this is what the function is. And so my derivative, well, 5 times 2, 10x to the 4th, minus 5 times 3, 15x squared. Done. By the way, if you're curious, do the derivative of x cubed, do the derivative of 2x squared minus 5, and multiply them together. Spoiler alert, you will not get this. This is correct. But again, more on that on Monday. Another example that you're going to see, and by the way, I'm going fast. I realize that I'm going fast, but I also realize this is a video that you can pause and rewind and rewatch and slow down. So if you need to do that, go ahead and do that. Another thing that you're going to see is something that looks like this. Just like we don't know what to do with products, we don't know what to do with a quotient either. What's the derivative of this thing divided by that thing? Again, I'm ruining Monday for you, but spoiler alert, it is not the derivative of the numerator divided by the derivative of the denominator. It'd be nice, but it's not true. So instead of taking the derivative, I'm going to rewrite this in such a way that I can differentiate. Specifically in this case, I'm going to divide all of 3 of these terms by x to the 3rd power. I'm going to do 4x to the 4th divided by x cubed. That's 4x. I'm going to do 3x squared divided by x cubed. That is 3 over x, that'd be the same thing as 3x to the negative 1. And then 8 over x cubed, that would be 8x to the negative 3. I know how to do the derivative of something times x to the some power. And so now I've got it in a form that I can differentiate. Let's go ahead and do that. The derivative of this is, well, the derivative of 4 times x is 4 times x to the 0. I've got, let's see, minus 3. Let's see, when I do the derivative, I'll have negative 1 times negative 3. That'll end up being plus 3 x to the negative 2. I'm doing negative 1 times 3 to get negative 3. I'm subtracting negative 3, making that a positive 3. And then finally, I have 8 times negative 3, negative 24, x to the negative 4. You'll probably be thinking of this as bring the exponent to the front and lower the exponent by 1, or some phrasing like that. And then for something like this, because I was given the problem with all positive exponents, I think it's reasonable for us to simplify this in the same way. I'm going to call this 4 plus 3 over x squared minus 24 over x to the 4th. If you want to combine these all into one big fraction, that's okay, but I would say this is simplification enough. At what point does this function have a horizontal tangent line? We'll see problems like this. We're going to see a lot of problems like this. Well, if there's a horizontal tangent line, that means the derivative of this is equal to 0. So let's find the derivative of this. It's already in a polynomial form, so I don't need to do any rewriting. Derivative of 4x to the 3rd is 12x squared, minus 3 times 2 is 6x to the 1st, minus 18 times x to the 0, and the derivative of 15, the derivative of a constant, is 0. So I will have a horizontal tangent line when my derivative is equal to 0. So let's set it equal to 0. 12x squared minus 6x minus 18 is equal to 0. I'm going to divide everything by 6. And 0 divided by 6 is still 0. So I can do that. Let's see, if I'm going to solve this, I'm hoping that this is factorable. If it's going to be factorable, then it's going to have to be 2x times x to give me 2x squared. It's going to have to be 3 times 1. It's just a question of which one's positive, which one's negative. Let's see, I need to have a 1 in the middle. So if I put the 3 here, I'm going to have 2x times 3 and 1 times x, and that's going to give me not a difference of 1. I don't think the 3 is going to go there. I must have to put the 3 over on this side, and the 1 would have to go there. So I'll have a 3x from these two terms. I'll have a 2x from those two terms. I need my middle term to be a minus 1, so it must be minus 3x and plus 2x. And so there's my factored form. So that means this will be equal to 0. Remember, we're looking at the derivative right now. This will be equal to 0 when x equals 3/2, or when x equals negative 1. If you're curious, graph this function, graph this whole mess of stuff right here, this cubic polynomial, and then take a look at the behavior of the graph at x equals 3/2, 1.5, or x equals negative 1, and you will see that those are places where the tangent line is horizontal. Moving right along, a couple other types of problems that you're going to see. Find an equation for a line that is tangent to this curve at x equals 1. I'm actually going to skip this one. Let's take a look. I want to do a tangent line, but I also want to do something else that may be a new term for you. So this is the same as the problem that I just put up. You'll have plenty of time to practice these in your homework. Find an equation for a tangent line to this function at x equals 3. Well, here we go. I need the derivative. The derivative of f is, here we go, 2x cubed. So it'll be 2 times 3, 6x squared, minus the derivative of 8x is 8x to the 0, or 8. So there's my function. I need the value of the function at x equals 3. So I just plug in 3. 6 times 3 squared, 6 times 9 is 54. 54 minus 8 is 46. But then if I want an equation for a tangent line, I don't just need the slope, I also need a location. At x equals 3, well, in addition to f prime of 3, let's find where this function is at x equals 3. And if I plug 3 into the function, I've got 2 times 3 to the third. 2 times 27 is 54. 8 times 3 is 24. 54 minus 24 is 30. I hope I'm doing that right, but I think that's right. And so if that is what this looks like, I need to just move this out of the way. I've got the slope at x equals 3. I've got the location at x equals 3. I suppose I could say that it goes through the point 3, comma 30. And so my equation for the tangent line is y minus the y value equals the slope times x minus the x value. And there we go. That is the slope, the equation of a tangent line at x equals 3. A normal line, this may be a new term for you, but normal is another way of saying that it is a line that is perpendicular to the tangent line at that point. And I'm sure I'll go over this again when we get to, when we talk about different curves and trajectories and things like that next semester. But for us right now, normal actually may be a term that maybe you haven't seen it in physics yet, but it'll come up sometime this year when you're doing lenses and refraction and things like that. But normal, you can think of it like perpendicular. It's not exactly the same thing, but we can think of it the same, which means the only thing that changes is the slope. It still goes through the same point, but now my slope, instead of being 46, my slope is the opposite reciprocal of 46. So my answer is just y minus 30 equals negative 1/46, x minus 3. Quick and easy to do because all I'm changing is the slope. I'm changing the slope to the opposite reciprocal. Okay, again, I realize this is rapid fire. We're covering a lot of material, but this is very procedural. Hopefully, if we have questions, we can take a look at them on Monday, but I think I've mentioned before, we need to get going, and today's a good opportunity for us to do that. Exponential functions. I'm actually going to pop over to Desmos for this part, so I'll be... Okay, here we are in Desmos. Right now I have a graph of 2 to the x. So I want to think about what the graph of the derivative of an exponential function would look like. On Monday, we looked at the derivative as a function. So we looked like over here, the function is increasing, but ever so slightly. So it's going to be a slightly positive number, just barely above the x-axis, like the function itself is. And as I move farther, it starts to increase a little bit more quickly. So the derivative here, the slope of a tangent line back here, maybe x equals -2, it's still positive. It's a little bit larger, just like the function is. And as I keep going, as the function gets larger and larger, it gets steeper and steeper. So the derivative would be getting larger and larger, just like the function is. The behavior of the derivative seems very similar to the behavior of the function. Now I'm going to turn on, you see over here, I've got the function is 2 to the x, and I've also got a graph of the derivative that I don't have on right now, but I'm going to turn it on and take a look at that. And we see that the behavior, the shape of the derivative curve is really similar to the shape of my exponential function, which we kind of had figured out already. So the graph of 2 to the x lies above its derivative. It's a little bit bigger, but the shape is definitely extremely similar. I'm going to change that 2 to a 4 just to see what that looks like. And what we see is similar behavior. It's still an exponential function, but here we see that the derivative, while it still has the same shape, it's on the other side. The derivative of 2 to the x lies completely underneath the graph of 2 to the x, but the derivative of 4 to the x lies above it. Now, what this tells us is that there must be some number in between 2 and 4 where it crosses over, where it switches from being less than the function to being more than the function, or vice versa. And so what I'm going to do is I'm going to make a slider. I'm going to just call this a to the x. That way, I can move this around and you can see the function just barely changing. Maybe I'll zoom in a little bit so we can see it a little bit more sharply. So as I'm changing the value of x, we see that the shape of the graphs are slightly changing. Here, for values around 4, from 3 to 5 is what I'm showing you right now, the derivative graph lies above the function. But if I switch down over here to the other values, numbers around 2, I see that the derivative graph lies underneath the value or the original function. And so there must be some number somewhere in between, and I'm just kind of bouncing around, zeroing in on it. Looks like it's somewhere right around, well, maybe about 2.7, 2.71, 2.72. And we could keep messing around with this and fine-tuning this. I suppose I could zoom in on the function and get really close to it so I can really see the difference between these two. But what we would find out if we zoomed in, if we really got down to examining this thing on a very close level, is that this magic number, this 2.7 something, well, some of you may be thinking it already. It turns out to be the number e. And this is one of the definitions of the number e, is that e is the value, e is the constant, such that the derivative of e to the x is e to the x. And I guess that's all I needed to use. And so what we learned from that is that the derivative of e to the x is e to the x. So I guess I'll write it as the derivative of e to the x is e to the x. And I realized that what you just witnessed was far from mathematical proof. What you just witnessed was me saying, well, it looks like it's about the same. It looks like there's this number. But I'm going to say that, again, a definition of the number e is that the number e is the constant such that the derivative of e to the x is e to the x. And so, in summary, everything that we did today, I'm going to put it all on one slide. I will post this slide on Schoology so you'll be able to access it and take a look at everything that we've done. But here's the bottom line. The derivative of a constant is 0. The derivative of a constant times a function is the constant times the derivative of the function. We can just treat the constant separately. This is really useful, and it'll be reinforced on Monday. The derivative of a difference, the derivative of f minus g is equal to the derivative of f minus the derivative of g. And if I add some plus signs, it doesn't change anything. I should probably add the right color plus signs. We hate to mix our blacks and blues. The derivative of f plus g is f prime plus g prime. The power rule is the one that's next. The derivative of x to some power is that power times x to the power minus 1. And then finally, the derivative of e to the x is e to the x. I'm glad MEA break is right now because it's going to give you a couple days to get some practice to let this stuff sink in. I do have an assignment that is due on Monday. If there are some questions that we need to take a look at, I'm okay with that. But this is your opportunity to get lots of practice. Practice taking derivatives. This skill needs to become secondhand nature where it's just automatic. These derivatives in this time next week, it'll just be simple, easy stuff that we will then be applying to other more important and more complicated stuff. A whirlwind. If you need to watch this again, certainly watch it again. Sorry, got a little bit on the long side, but it was important to me that we start moving through this chapter. I want to really spend time doing stuff that's more complicated than this. And most of what I did today was just showing you where this stuff comes from. This slide is really what's important. This slide is the stuff that you need to know, that you need to be able to do. So go ahead, get some practice. Come on Monday armed with questions for me, and we will move on at that point. Awesome. Great. Have a great day. I'll see you all on Monday.